All right, I want to do a derivation, and we're going to use this derivation for our torsion analysis. The derivation that I'm going to do regards uniaxial tension, and it's very straightforward. Consider our uniaxial tension test where we apply a load P. We have a cross-sectional area of the specimen that we're using, and the length, the original length of this specimen is L. After we load it with P, we get a deformation delta. Delta is the increase in length, change in length. And this particular material has a Young's modulus of E, which is the, if you remember, we have a stress-strain curve. Here's our stress-strain curve in the linear range, and the slope of that line is E, Young's modulus. So my E is a slope. It's a delta y over delta x. Our y is sigma, our x is epsilon. So we're going to get that our E is my sigma over epsilon. And you know already that epsilon, the strain, I guess I don't have it written down here, but it's the strain, epsilon well, I'm just going to put it down here, run out of space. Epsilon is delta over L, change in length over the original length. I guess I could move that. So defining these terms, what do we know? Delta is the change in length. P is the applied force. L is the original length. A is the cross-sectional area. E is the Young's modulus. Epsilon is delta over L. And so what do we have? We have we're starting again from the beginning. E is the slope, delta y over delta x. So E is sigma over epsilon. I manipulate this expression and I get sigma is equal to E times epsilon. I substitute sigma is P over A, sigma stress, force over area. Epsilon is delta over L. I plug that in. And then I solve for delta. I get delta is equal to PL over AE. So that's how we determine what the change in length of our specimen is, knowing this information. And this is an equation you should memorize. It comes in handy on the EIT exam or FE exam. Okay, having done this derivation, this is a very simple one because the geometry is extremely simple. And now I'm going to basically do a torsion. I'm not really going to do the derivation, but it's the same derivation, but it has different geometry again. And like I say, I don't want this to be a geometry class. So I'm just going to do a conversion between what we just did and then our equation for torsion. So these two equations in a sense, are similar. I get delta is equal to PL over AE. In torsion, we end up with phi is equal to TL over JG. This is the one I want you to memorize. Phi is equal to TL over JG. Now, what are all the terms there? Phi is the angle of twist. In other words, what do I mean by that? If I take this particular problem here, I have my cylinder anchored to the wall, and I apply a torque to twist this. And if we look at the end of this, suppose at the beginning I etch a line, a horizontal line from the left edge to the center, and then I twist it, and what I find is the original brown line shifts into the green line, or shifts into that location. So if I look at just the end, it starts there, but when then I twist it, it ends up there. And the angle between the original horizontal line and the final line, that angle we're calling phi. That's the phi is the angle of twist. L is the length of our cylinder. T is the applied torque. J, again, is the polar moment of inertia, which we've talked about. G now is what? It's not the modulus of elasticity, it's the shear modulus. So, if you recall what the shear modulus is, we talked about this before. But just as a reminder, if we did this experiment in the lab, in other words, I take a square with I'm going to call it a height L. I'm going to apply a shear stress tau. And if I apply that shear stress to that square element, it becomes a parallelogram, and it has a deformation defined in this manner, so that distance there, of delta. Then, by definition, we call gamma, the shear strain, delta over L. It's a little bit similar to epsilon, which we call delta over L, although delta over L with epsilon were defined differently, but it's the same equation. Now, a lot of times we don't say it, but in the same way that we have two kinds of stresses, and that's it, that's all you need to learn, normal stress and shear stress, we also have normal strain and shear strain. So you mostly use the normal strain, and you know that one well. Well, shear strain, same equation, different definition of the terms, but the same thing. So so you got normal stress and shear stress, you have normal strain and shear strain. So we can plot another stress-strain curve, but this stress-strain curve is shear stress and shear strain, not normal stress and normal strain. So, in other words, on the previous page, we did normal stress, normal strain. Here we are plotting shear stress and shear strain, and it's similar. The same result in a sense. It's a straight line. And we give the slope of that line the symbol G, which is the shear modulus. So shear modulus is similar to Young's modulus. So, okay, that defines all these terms. So in other words, this is our equation. Phi is equal to L over JG. Now, and what I derived before, so you can see the similarities. Delta is equal to PL over AE. Phi is equal to TL over JG. As I said, it's the same derivation, but different geometry. So I'm not going to derive the phi one. It's good enough for. So I want you to memorize this. Phi is equal to TL over JG. Okay. The easiest way to do this problem, or to understand what this is and how to use it, is with an example. And so I'm going to go back to the example that we already did. And these are the properties. It looks like that. We have, let's see. So our cylinder is mounted to the wall. I have 100 pound-inches there, 200 pound-inches there. This is 10 inches, 10 inches. Remember, we found the reaction by taking the sum of the torques in the x direction. We get our final free body diagram. We decided it was in equilibrium because I have 100 to the left plus 100 to the left means 200 to the left, 200 to the right. We drew our torque diagram where we go to the left, we go down, over, to the left again, down, over, to the right means up. So I get my torque diagram that's similar to drawing a shear diagram. But the benefit of this is as complicated as it gets. So in these problems, you're going to need to draw a torque diagram that is similar to the simplest shear diagram you can ever get, basically. So everybody gets the torque diagram. All you need to do is to remember left. If this is going to the left on the torque diagram, I go down. This is going to the left on the torque diagram, I go down. This is going to the right on the torque diagram, I go up. So, okay. Now, we're going to apply this phi is equal to TL over JG. Let me just talk about the units for a second. T is torque from the torque diagram. The units on torque are what? Pound-inches, for instance. L, of course, is length. Units on that, in this case, are inches. J, if you remember, is a moment of inertia term, which has units of inches to the fourth. Inches to the fourth. G is our stress-strain slope. It has units of stress because strain has no units. So the units of stress, pounds per square inch. And when we put in all the units, what do we get? We get dimensionless. Phi is dimensionless. Well, phi is an angle, so that means that our phi is in radians. We did this problem where we came up with J. I'm not going to do it. It's pi over 2 times C outer to the fourth. It's a solid cylinder, so we get that value of J. All right, so now we have this issue to a certain extent. We have our torque diagram. And what we learn, of course, is torque is not constant. It's negative 100 in that region. It's negative 200 in that region. So how do we handle that when we apply this TL over JG equation? It's very straightforward. We're going to break it. What we're going to be interested in is phi. We're going to call it phi from A to C. So here's point A, here's point B, here's point C. I want the angle of twist from across the entire length, A to C. And the way that we're going to do it is we're going to break up the A to C. It's going to be A to B and B to C. And that's how we're going to account for the fact that the torque diagram is different in the A to B region from the B to C region. So phi AC is going to be TL over JG for the AB region plus TL over JG for the BC region. So I look at my torque diagram. Well, so taking them one at a time. For A to B, the torque is negative 100. The L is 10. How do I get that? Because between A and B, it's 10. The J and the G don't change. So the J is 1.57. The G is 12, is given in this problem here. So it's 12 times 10 to the 6th PSI. That's for the A to C region, or A to B region rather. The B to C region, what do I have? The torque is negative 200. The length again is 10 inches. And then the JG are the same. I simply calculate out the value, and I get that phi A to C is negative 15.9 times 10 to the negative 5th radians. What is the negative? Now the negative sign has some meaning. Well, the negative sign means counterclockwise rotation when looking left. In other words, if I'm standing here and I'm looking left, what I find is that the rotation is counterclockwise in this particular case. So if I get a positive sign, if I get a positive sign, that means I have clockwise rotation. All right, I want to say something about the effect of hollowing out the rod or the cylinder shaft on the polar moment of inertia. Let's just do a little calculation. Suppose I have a solid shaft and I have a hollow shaft. They both have a 5-inch outer radius. The solid one has no inner radius. The hollow one has a 2-inch inner radius. What are the differences between the polar moment of inertia for these two cases? Well, the solid one is what? Pi over 2 times c out to the 4th. Plug that in, I get 981.7 inches to the 4th. If I take out the inner 2 inches, I go pi over 2 times 5 to the 4th minus 2 to the 4th. Pi over 2 times 5, the quantity 5 to the 4th minus 2 to the 4th. And the end result is that I get 957. Well, we compare 957, 981.7, almost no difference. So what do we see? The inner material really doesn't do much. And that's why most shafts will be hollow, or many shafts depending on. Why? Because we don't really need the inner portion. It really doesn't do much, and it saves on material costs, for instance. Okay. So in other words, you can see the numbers right here. Hardly any difference by removing the inner material. It's sort of like the concept here, a hollow shaft is similar to our I-beam in a sense. In other words, with our I-beam, the way that it works is we're pushing the material away from the neutral axis, and that's where it helps us. And the same thing with a shaft. The material away from the center does the most for us, and so that's where we want our material, is away from the center. Okay, similar problem, only I've had little complications here. And how do we handle that? Very straightforward. So again, I have a shaft anchored to the wall, and I've got 100 pound inches, 300 pound inches, 1600 pound inches. But on this particular case, notice I've hollowed out a portion of the shaft. So the right part of the shaft is hollow. The left part of the shaft is solid. We have an inner radius, an outer radius. We're going to have a point of interest right there at the edge. And the problem is to, one, draw the torque diagram. And we want to find, oops. I shouldn't have said this. So this is not given here. Okay. What I want to find is I want to find tau max. And I want to find phi 80. So we're going to use the expressions phi is equal to TL over JG, tau is equal to TR over J. First thing I have to do again is to find the reaction, just like we had to do with our beam problems. And again, so using the right-hand rule, I have 100 going to the left, 300 going to the right, 1600 going to the right. I've drawn TA like that. I look at this free body diagram and write this equation with going to the right is positive. Just add that. Going to the right is positive. And I have that, so I have TA, because it's go to the right, minus 100, it's to the left, plus 300, it's to the right, plus 1600, it's to the right. All that's equal to 0. I solve for TA, negative 1800 pound inches. That means I flip the arrow around. So it was going to the right, I show it to the left, show it with 1800. And then I check my answers. Going to the left, I have 1900. Going to the right, I have 1900, so that's in equilibrium. I draw the torque diagram, down 1800 because it's to the left, down another 100 because it's to the right, to the left, I mean. Up 300 because it's to the right, up 1600 because it's to the right. Start at 0, end at 0. And just okay. So I have our torque diagram, and let's start with find tau max, TR over J. Well, what do I have to do? Well, I have to look for the maximum torque. Well, it could be a couple things. We have to look in a couple places. Notice I have my hollow shaft here, and I've got my solid shaft there. So I have to keep that in mind when I'm looking for my maximum tau. In this particular case, what do I see? I have my maximum torque in this region, and what do I know? Well, that region is this region, and it encompasses both the solid portion and the hollow portion. So where is my tau max going to be? And sort of, I need to find my maximum torque. Well, it ends up because I have the shaft is hollow here, my J will be a little bit smaller in that region, meaning, and J is in the denominator, and therefore my tau max is going to be in that region there. So my point of interest is going to be here. And then because I know that the maximum shear stress occurs at the very edge, that I get my point of interest at the edge. So when I do my tau max equals TR over J, there's my point of interest, so I use negative 1900. My R is going to be 2 inches because that's the distance from the center to my point of interest. And then my J is simply pi over 2 times C out to the fourth minus C inner to the fourth. So again, when we're looking for tau max, you have to find the point of interest. And notice, before I flip the page here, that I have these regions for my shaft. I have A to B, B to C, C to D, D to E. So I have all those regions. So that when I do my phi A to E, I have phi AB plus phi BC plus phi CD plus phi DE, which means I have my TL over JG for AB, TL over JG for BC, TL over JG for CD, TL over JG for DE. And now it's just simply a plug-in. So, first I notice that JAB equals JBC, which is pi over 2 times 2 to the fourth. And JCD equals JDE, which is pi over 2 times 2 to the fourth minus 1 to the fourth. So I get those J's. And then now I have to look at the different L's. So LAB is 4, LBC is 6, LCD is 6, LDE is 4. And basically you can follow through this, and I just plug in all those values here. The G is given to be 12 times 10 to the 6 psi. And when I do all this calculation, I end up with phi AE is minus 1.24 times 10 to the negative fourth radians. Again, the negative sign means it's counterclockwise when looking left. All right, so I want you to pause the video and do this problem. And I will go through it quickly. Okay, I assume you've paused it and you've done this problem, and here is the solution. And I'm just going to go the same problem, so I'm not going to go through it in too much detail. You can check the answer by pausing the video here and looking at all the calculations. But what do I have? Again, I have AB, BC, CD, that 20 is using the right-hand rule to the right. That 30 using the right-hand rule is to the left. That 60 using the right-hand rule is to the right. I put on my TA and take the sum of the torques. I get TA is negative 50. So I get this. I add up. Going to the left is 50 plus 30 is 80. Going to the right is 60 plus 20, 80. So it's an equilibrium. Draw my torque diagram. Down 50 over, up 20 over, down 30 over, up 60. So again, we want to find, now in this case I have find the tau at the point of interest, and I've given you the point of interest. Point of interest is there, and the point of interest is there. So the point of interest is at 4 inches from the center, and it's in the BC region. So tau is TR over J. My J is solid there, so it's pi over 2 times 5 to the 4th. At my point of interest, oops, between B and C, I'm here. I have a torque of negative 30, so I put that in there. The point of interest is given at 4 inches, that's 4 over the 981. So I get tau is negative 122 psi. Or negative 0.122 ksi, because I was doing kip inches. Okay, now here's a separate problem here. And I said, suppose the torque diagram is this, and we're asking you to find tau max for this. Okay, so other dimensions are the same, but so I'm at negative 50, then negative 30, then negative 45. What do I have to, I've got a dilemma here. And my dilemma is this. So in other words, I have this shaft, but I have different loads, and I end up with a torque diagram that looks like what I just showed here. And my dilemma is this: it's negative 50 in this region, it's negative 45 in this region. If I'm looking for tau max, what's the problem? It may not be here. Why? Because the shaft is solid in this region. The maximum may be in here because the shaft is hollow. So I have to just double check. So I don't know whether, because these two numbers are close, right? The negative 50 and negative 45 are close, and I just have to do the numbers to figure out which is worse. So I'm going to do, if this were the problem, then I have to find tau max in the region AB, and I have to find tau max in the region CD, and compare the two. So I take the negative for the AB, negative 50, and now what? My C outer is 5 inches. That's where my maximum is going to occur. So it's negative 50 times 5 over 981. That stays the same. Or not stays the same, that's what we already calculated. And that's for AB. In CD, I have the negative 45, because negative 45 there, I'm going to have the 5, and the J in that region is only 957, so I get this number. So I have to compare those two numbers. I don't know which one is most critical till I put the numbers on it. I compare them, and I get that tau max is in the AB region. It's similar to what we did with beams, that you have to be a little bit careful in finding the stresses, finding the maximum stress sometimes. The last part of this problem, we have phi AD is equal to phi AB plus phi BC plus phi CD. We're going to apply phi is equal to TL over JG, and it's just a plug-in. So I'm not going to go through this. I plug in all the values using the torque diagram, and I get this result. Hopefully you got it when you did the problem. If we were to ask, no, okay. All right, I'm going to stop there.